I apologize for how crumpled these are. I didn't have any extras with me, so I just took old maneuvering boards I used for problems, and I just, erased the work to make it, to give myself a clean slate, but obviously it's still, wrinkled. However, this is a maneuvering board. This is what the Navy primarily uses because it's like the official government version of any type of maneuvering sheet. However, I'll grab my computer here. I pulled up I found online a picture of a radar transfer plotting sheet because I kind of couldn't find a very good one, but these are what radar transfer plotting sheets look like. They're essentially identical between the two. I'll go into more detail about the maneuvering board and then I'll get back to the plotting sheet in a second. However, this is just what we use to plot all radar problems. And you can see it's designed to be reminiscent of a radar scope because radar scopes should always be circular with a bearing ring all around the sides. And then a nice clear fixture in the center here to represent our position, because as long as we're working with relative motion, no matter what, our ship is always right here. There will be some problems where we deviate from that, but 90% of the time, this is our location and everything else is just moving around relative to us. You can see a compass rose all around the side of the circle here. And in addition to the true bearings in all these directions, you've also got smaller letters here. What these are is these are the reciprocal bearings. So you can see if 230 goes this way, it says 050 in the smaller letters. What that means is if we follow this line across and into the opposite direction, we get to 050. It's the exact opposite angle from 230, which is why 230 is written in little letters here, just to show you if ever you need to know what the opposite, what the reciprocal course would be, it's already written down for you, at least on the 10s. These little boxes here are just so you can record the information for a contact real quick when you scroll over to the radar scope and you write down and you take the time and what its bearing and range is. You can just copy them down on the sides here. They're in all four corners. What you've got on this, before we get to that, here you can just see a scale marked up just from 0 technically being the center of the scope, and then 10 is also not marked, but it's just the outer edge of the circle, and then delineated into tenths along the way, 1, 2, 3, 4, and so on. It doesn't matter what that is, what units you use for that. Typically, especially in amongst mariners, this is going to be nautical miles. So this right there, here would be representative of a 10 nautical mile range around your ship. In the Navy, this could be set up as yards. So instead of being 2 nautical miles, this would be 2,000 yards. That way they can work in yards if that's what they prefer. You could use this in feet and it would all technically be accurate because all they are is proportional to one another. They're not proportional to any scale outside of it. It doesn't matter. It's just whatever you want to use. And again, the Navy tends to use yards while the Merchant Marine will almost exclusively use nautical miles. Some people might even use cables for all we know. However, if you wanted to convert that to other scales, you've got them right here. So you can see 4 to 1 and 5 to 1. And then on this side, 2 to 1 and 3 to 1. Because if we're assuming that this right here is our 1 to 1 scale, 1 block here is worth 1 block, then this right here is how we could convert that to a 2 to 1. It runs the full span from the bottom of the circle all the way to the top, and just sets that up if each of those nautical miles listed here were actually 2. Same with 3, 4, and 5. just in case you're working with contacts really far away from you, proportional to the units that you're measuring. Now, most commercial radars are set up with scales in units of 3. They could go from 1.5 miles out to 3 miles out to 6 miles out to 12 miles out to 24 to 48, though you would never really use 48 miles. That's almost every single one is set up in multiples of 3 like that. So a 10-mile scale is almost kind of unhelpful, because if you're most of the time using your radar on the 12-mile scale, then the very furthest contacts are actually not visible on it. And if you're using it on the 6-mile scale, then the outer portion of your plotting sheet here is totally unnecessary, because you only come out to 6. And so that's why somebody might use the 2-to-1 scale if they're on a 12-mile range, just so they can have up to 20 total miles on the plotting sheet that they're working with. Now, finally at the bottom here, you can see 3 scales here. What this is a logarithmic, I think it's just called a logarithmic time scale, or time, speed, and distance scale. This is for converting time to speed to distance. It's actually just it's just 60 D Street, but redepicted in a graphic sense, as opposed to, a mathematical sense. It operates in the exact same way. This is the biggest difference between the maneuvering board and the radar transfer plotting sheet, because they set up their logarithmic scales differently. I wish that the photo I had was a little less blurry, but you could see in the plotting sheet down here, it only uses a single scale that runs across it, and that single scale can be interpreted to represent time, speed, or distance. I actually think that the maneuvering board scale is a lot easier to work with, and I'll get into how to use it later on, but it's very simple. You just connect the dots. Look, if you spent 6 minutes sailing and you sailed 2 miles in that time, 2 miles in 6 minutes, if you connected the dots, would take you all the way to 20 knots right there. You actually do just mark one point, another point, connect them, and find where that lands you in the 3rd scale. On the plotting sheet, what you would do is you would measure out your dividers. If you had a distance and a time, you'd place one divider on where your time fall or where your distance falls. So I think it would be on this side. You place one time where your distance falls, so that would land on 2 for 2 miles, and another time on 6 for 6 minutes. Get that distance between the two, bring it over to the 60, and then place the other time, preserving the same distance you had before, and where it would land on the 20, meaning that if you went 2 miles in 6 minutes, you would get 20 total knots. So just the left-hand side time is always time, the right-hand time is distance, and then you bring it over to the 60 and drop it on the time. It's a little more difficult to use. It'll take some time. I wish I had one physically with me, because then I could show it to you better, but it's not that complicated, and ultimately all you're doing is 60 D Street. So if you ever need to back yourself up, if you're not confident that you did it right, just take out a pencil and paper and you do the 60 D Street problem, and you should be able to get the same solution. Other than that, the plotting sheet is, you can see, more or less identical. It's set up in the same way, it just doesn't have those bearing lines along it, which I think the bearing lines are nice, but this one doesn't have it, whatever. It still has the scales on the side. You can see, I think here's a 3-to-1, a 6-to-1. Actually a 0.5, a 1-to-1, 2-to-1, 4-to-1. and so on. It's a little more, or there's a little less to it. It's a little more bare bones. I do personally like the maneuvering board more, but if you use one, you can use the other. It's not complicated. They're essentially doing the same thing. And given some time, you will get very used to how to use these. They're really not that hard. They're just kind of intimidating at first because there's so much going on and they seem so complicated.